Although I may have been gone for a short forever, I am back. So, welcome back to another video where we are going to be finding the residues of the gamma function. So without any further ado, let's get started. First off, let's actually discuss the domain of the gamma function, right? Because it's not actually defined for all real numbers. The domain of the gamma function is as follows. So we can say, that's an F. Great start. We can say that gamma of some z, this is defined for all real numbers, but just excluding all negative integers, including 0. I know 0 is a negative, but 0 and all negative integers. So this right here is the domain of the gamma function. So the residues, or the points at which we're going to be finding the residues at, are going to be, well, precisely this, the places where it is undefined, where all the negative integers along with 0. So that's actually a pretty good starting point. This right here, the 0. So what is the residue of gamma of some z at 0? Well, we have this handy dandy definition that I pasted right here. So let's use that. We know that z naught in this first case, so this is case 1, or I'll call it case 0 actually. We're going to say that z naught is equal to 0. Equals 0. So for the case z naught equals 0, what do we have? Well, the residue for our gamma, or the residue of our gamma function, residue of gamma at 0, well, I'm just going to scoot this on over. What this is equal to is going to be the limit as z approaches 0 of z, because, well, this z naught right here is just 0, so z times our function, which is just going to be gamma of z. So we have the limit as z approaches 0 of z times gamma of z. And what is that right there? Well, if we just plug in 0, we don't really get anything special. I mean, we get 0 times infinity, which doesn't tell us anything. But if we use one of the properties of the gamma function, namely the fact that z times gamma of some z is equal to gamma of z plus 1, well, we can see that whenever we plug in 0 into this, well, we don't get 0 times some sort of infinity. What we get is gamma of 1. So this right here is just going to be gamma of 1, which is equal to, drum roll, just 1, actually. So we've done it for z naught equals 0. Let's do it for, or let's find the residue at 1. So let's say z naught is equal to 1 now. Z naught is equal to 1. Okay, so the residue of gamma at 1 now. Well, this right here is going to be the limit as z approaches 1 of z plus 1, or pardon me, as z approaches negative 1, pardon me. It's going to be plus right here because our z naught is equal to negative 1, so this right here really should be negative. So we have the limit as z approaches negative 1 of z plus 1, and then times gamma of some z. And we don't exactly have this identity ready to go. We can't just exploit that immediately. So what we're going to do is actually just multiply the top and bottom by z. So multiply top and bottom by z. And what this does is it allows us to express the numerator as follows. We know that gamma of z times z, so this right here, is just gamma of z plus 1. But then we also see that we have a z plus 1 right here. So what we have is a gamma z plus 1 times z plus 1. Well, that's just going to be the argument of whatever's in the gamma plus 1. So in this case, it's going to be z plus 1 plus 1. So what we have then is equal to the limit as z approaches negative 1 of gamma of z plus 2 this time, but then just divided by z. And we can just plug negative 1 into this right here because we know that gamma of just 1, because whenever we plug in z as negative 1, we just get 1, the argument there. What we get is just gamma of 1, so 1, and then just divided by negative 1. So this whole entire thing right here, we don't even need the fraction bar, we can just write as negative 1. So I'll do maybe a couple more, and then we can just do this in general. Let's find the residue at 2. So we have z naught is equal to 2 now. So the residue is going to be equal to the limit as z approaches negative 2 of gamma of z times z plus 2. And let's just do the same thing as last time so we can continue exploiting this little identity right here, or the z times gamma z is gamma z plus 1. So what I'm going to do is multiply the top and bottom by z and then z plus 1. all divided by, z and then z plus 1, because that does need to equal 1. And what we can do now is express the numerator as, well, if we just kind of group this stuff together, we have this right here, that's gamma of z plus 1, and then grouping this and that together, we have gamma of z plus 2, and then grouping these together, so what comes out of that in this right there, we end up having gamma of z plus 3. So what we have in total is gamma of z plus 3, and then divided by z times z plus 1, so z and then z plus 1. And then, of course, we have our limit here, so limit as z approaches -2. And what do we get here? Well, in the numerator, we still get our gamma of 1. This seems to be a common theme here, so just a 1. And then divided by, well, what happens when we plug in -2 in the denominator? Well, we end up with a -2 times a -1. So that's just going to be a 2. So just 1/2. So for the general case, we can say that z0 is going to be equal to some number, so we can just call this n, I suppose, or really -n. This will make everything a little bit nicer, actually. If we let z0 just equal -n, where n is just a positive integer, so now it's greater than or equal to 0. If we let z0 equal -n, what we have is the residue of gamma at -n is going to be equal to, well, gamma of z, but then, or really we have a limit out front, I should write that. The limit as z approaches -n of z plus n. This is why I had the negative here, actually, because that way we have like z plus n. So how can we simplify this right here? Well, using the same techniques as the couple times before, we can just multiply the top and bottom by just a very long polynomial, right? We can just say multiply the top and bottom by z, and then times z plus 1, and then dot, 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 all the way to z plus, well, some n minus 1. And then same thing in the denominator, right? Because we do need to be multiplied by 1, and this does need to cancel out. So dot, 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 z plus n minus 1. So what do we have in the numerator? Well, we can just do what we did before and just kind of group all of our terms in a way. So we can say that this gamma of z times z, this is going to be gamma of z plus 1, so gamma of z plus 1. And then we can say the gamma of z plus 1 times z plus 1 is going to be gamma of z plus 2. And we can continue doing this all the way up to this term right here, z plus n. So what we're going to be left with in the numerator is just going to be gamma of z plus n and then plus 1. So what do we have in the denominator? Well, in the denominator, we have z times z plus 1 times z plus 2 times z plus 3, and so on and so forth, all the way up to z plus n minus 1. So what just happens if we plug negative z into all this? So we actually write the denominator, z and then z plus 1, dot, 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 z plus n minus 1. What happens when we actually take the limit here? Well, in the numerator, we just get 1, because gamma of 1 is just 1, still. We have 1, and then, what's our denominator? Well, starting with this term all the way over on the right, if we plug in negative n, well, we just have negative 1 right here, so we have negative 1. And then if we take the term before that, so that would be z plus n minus 2, we have, well, just negative 2. And then if we continue this, we're going to have times negative 3 times negative 4, all the way up to, well, whatever this z is right here, and that would just be negative n. So we have 1 over negative 1 times negative 2 times negative 3, dot, 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 all the way to negative n. And if we just count how many terms we have, we can really just take care of the minus sign and express that as an exponential of negative 1. So we can say that this right here, we have n terms, because, I mean, they're literally numbered 1, 2, all the way up to n. So we have n terms. So if we just factor out all the negatives, what we have is just negative 1 to the n. And then we have, or what's left, is just 1 times 2 times 3 times 4, and so on all the way up to n. Well, that right there is just the definition, or at least the integer definition for factorial. So this right here is just going to be n factorial. So that means, in general, our residues of the gamma function are going to be -1 to the n divided by n factorial. And that right there, as I just said, are the residues of the gamma function for some number n, or for some integer n, I should say. So I hope you all enjoyed this video, and I will see you in the next one. Thank you for watching.